Let's start by enjoying some images of planetary nebulae, those translucent, often very colorful clouds of gas surrounding a newly emerged white dwarf. You can think of a planetary nebula as a sort of retirement party for a star, celebrating the end of its fusion-powered career. In this lecture, we'll tell the entire life story of a star, which begins with a different sort of nebula, a dark nebula. These are beautiful in their own way. They may lack color, but by obscuring the stars in the background, they have an unusually vivid three-dimensional appearance. Dark nebulae are the raw material for stars. They're clouds of hydrogen and helium, along with a small percentage of heavier elements, including grains of dust. The dust is what makes the clouds dark. Dark clouds are stable for millions or billions of years, but occasionally something causes part of a cloud to get a little too dense, maybe from a collision with a different cloud or from a nearby supernova explosion. When that happens, the increased gravity of the dense region attracts the surrounding gas, amplifying the density still further. The cloud begins collapsing. It fragments into clumps of different sizes, which eventually become stars of different masses. As we'll see, a star's initial mass determines just about everything that happens next. The most common type of star has about a third of a solar mass, but you also find stars with up to 100 solar masses, which emit such powerful radiation that the surrounding gas gets pushed away by radiation pressure. We're going to study stellar evolution, the way stars change with time, from two different perspectives. First, we'll sit right in the center of a star and watch the events unfold. Then, we'll view those same events from the outside. We'll see how the external appearance of a star changes with time. Let's get started by diving down to the core of a star. The two properties we need to keep track of are its temperature and its density. As usual, it will help to make a logarithmic chart, central density against central temperature, with density ranging from 1 to 10 billion grams per cubic centimeter, and temperature ranging from 1 million to 10 billion degrees. To get oriented, let's plot the data point for the Sun. We've seen that the Sun's core has a density of about 100 grams per cc and a temperature of 10 to the 7 degrees Kelvin. That's the ignition temperature for hydrogen fusion. We expect all main sequence stars to have that same core temperature, since they're all fusing hydrogen into helium. So let's draw a vertical line going through the Sun. That's the hydrogen fusion line. Any main sequence star will have core properties falling somewhere on that line. The ignition temperature of helium is higher. It's about 10 to the 8 Kelvin. That's because helium has a higher electric charge than hydrogen. It takes more energy to overcome the electrical repulsion and get the nuclei to fuse into carbon and oxygen. So in our chart, any star that's fusing helium in its core will appear close to a vertical line at 10 to the 8 Kelvin. Likewise, fusing carbon and oxygen to make heavier elements requires an even hotter temperature, around 10 to the 9 Kelvin. In general, the heavier the element, the hotter the ignition temperature. We could keep drawing more vertical lines at higher temperatures for fusing even heavier elements, but these three are enough to get the idea. By the way, the chart we're making should be understood as a schematic. The positions of these lines and other details are only approximate. I've done my best to omit the needlessly complicated details while still conveying the essential physical concepts. Now, with these landmarks in place, let's think about the fate of the Sun. It's happily fusing hydrogen into helium at 10 to the 7 Kelvin, and will stay at that point while the hydrogen lasts. But what happens when the hydrogen runs out? Without fusion to replenish the energy the star is radiating, the core begins contracting. Its density increases. Contraction also liberates gravitational potential energy, which is converted to heat, raising the temperature. It's that weird thing about gravitationally bound systems that I described last time. You let them lose energy, and they heat up. So the temperature and the density rise, causing the point representing the sun to move up and to the right. We can figure out the exact trajectory of the point on our chart by using the fact that the star is still very nearly in hydrostatic equilibrium. That may require some explanation. The star is losing energy, the core is shrinking. So how can it be in hydrostatic equilibrium? The point is that the loss of energy is a long and drawn-out process, lasting millions of years. We worked out that timescale a couple of lectures ago. It was Kelvin's erroneous estimate for the lifetime of the sun, based on the premise that all of its power came from gravitational contraction. The energy loss is so slow that at any instant, the star is extremely close to equilibrium. The pressure may be changing over millions of years, but the star's mass distribution adjusts itself on a timescale of hours to strike a temporary balance between gravity and pressure. This kind of situation is called a quasi-equilibrium, and it comes up all the time in physics. Whenever the timescale for an event for a system to reach equilibrium is fast, but the conditions that determine the equilibrium state are slowly changing. The upshot is that we can calculate a star's path on this chart by using the equation of hydrostatic balance. We'll dust off a result that we derived a couple of lectures ago. M over R is proportional to the central temperature. We got that by setting the pressure required for hydrostatic balance equal to the ideal gas pressure. We use this equation to show that for stars on the main sequence, which all have the same Tc, R is proportional to M. But now we're talking about stars that aren't fusing hydrogen anymore. There's no reason for the central temperature to be a constant. But as long as we're near equilibrium, it will still be true that M over R is proportional to Tc. Let's write that in terms of central density instead of radius. We'll start by cubing the equation and writing the left side as m squared times m over r cubed, because that way we recognize the second factor as being proportional to density. Although strictly speaking, m over r cubed is proportional to the average density, not necessarily the central density, but it's a decent approximation to assume that the central density is always higher than average by the same factor. In which case, we can rewrite the equation as m squared times rho c is proportional to Tc cubed. Solving for rho and then taking the log, we get a straight line with a slope of 3. So that's the line that the core of the sun will follow in our chart once there's no hydrogen left, toward higher density and a hotter temperature. In fact, we can extend that line back into the past, too, to represent the early days of the sun, before fusion began. So let's back up and start the story then. When a star condenses from a glob of galactic gas, it starts out with low density and low temperature. Gravity draws it together, the core contracts and heats for millions of years until the center reaches 10 to the 7 degrees. Then the hydrogen ignites. The energy erupting from fusion in the core comes into balance with the energy being lost at the surface. The star has joined the main sequence. That's where the sun is now and where it will remain for another 5 billion years. Then the core runs out of hydrogen. It's nearly pure helium. Fusion fizzles out. So the core starts contracting again, proceeding further up a diagonal line with a slope of 3. The temperature rises until it hits 10 to the 8 degrees. That's hot enough to ignite the helium. This new power source halts the contraction and allows the star to linger a while, but not for billions of years. It's more like tens of millions of years. The helium fusing phase can't last as long because helium fusion isn't as efficient. On the chart of binding energy per nucleon, helium is closer to the peak than hydrogen. So there isn't as much energy to be liberated by fusing helium. The liberated energy per unit mass is only 1/10 as much as from fusing hydrogen. Can you guess what happens next? The helium gets used up. The core becomes pure carbon and oxygen. Fusion fizzles out again. Gravitational contraction resumes. The star moves further up the diagonal line. If it reaches 1 billion degrees, the carbon and oxygen ignite, again pressing the pause button on the collapse. And so on and so on. The core fuses heavier and heavier nuclei, each one lasting for less and less time, burning with increasing desperation. But wait a minute, there's something important missing from the chart, something that will alter the fate of the sun, something that we learned about in the last lecture: degeneracy pressure. The equation governing the sun's trajectory, that diagonal line with a slope of 3, came from assuming that the star is supported by ideal gas pressure. As the density keeps rising, though, at some point degeneracy pressure becomes more important than gas pressure. When does that happen? We can find out by setting the equation for degeneracy pressure, which varies as rho to the 5/3 power, equal to the equation for ideal gas pressure, which is proportional to density times temperature. To keep things simple, we won't keep track of all the constants, we'll just keep track of how rho depends on T. After some algebra, we see that on that boundary between gas pressure and degeneracy pressure, rho varies as T to the 3/2 power. That corresponds to a straight line with a slope of 3/2 on our log chart. To find the y-intercept, we would have needed to keep track of all the constants. When you do that, you find that the boundary line runs from about 10 to the 2 to 10 to the 8 grams per cc, as the temperature runs from 10 to the 6 to 10 to the 10. Above that boundary, degeneracy pressure dominates. But wait, we forgot something again. Last time we learned that degeneracy pressure doesn't always go like rho to the 5/3. When the density approaches that critical density of several million grams per cubic centimeter, the pressure starts growing like rho to the 4/3. The change in behavior is because the electrons are squeezed so tight they're moving close to the speed of light. So we need to modify the boundary line. Above the critical density, the slope of the boundary line is defined by setting rho to the 4/3 to be proportional to rho times T, the ideal gas pressure. In that case, when we solve for rho, we get that it goes like T cubed. The slope is twice as high as before, so the effect is to make a kink in the boundary line at high density. Now that we've established the domain of degeneracy pressure, let's restart our solar mass star at low density and temperature. It starts contracting and works its way up the line, pausing to fuse hydrogen, then contracting until the helium ignites. But now we see that after the helium runs out, it doesn't advance to carbon ignition. Contraction brings it into the degeneracy zone, and degeneracy pressure halts the contraction. Since degeneracy pressure doesn't depend on temperature or the energy content of the gas, the core can achieve a stable and eternal balance between pressure and gravity. No fusion required. The star becomes a white dwarf. The white dwarf is still losing energy through radiation, so the temperature goes down. That means the point moves straight leftward on the chart. The white dwarf cools off and goes dark over billions of years. All of that was for a star of 1 solar mass. Now let's back up to the beginning and follow the progress of a less massive star, say 1/10 of a solar mass. What will change? Well, let's see. The trajectory of a star on this chart was dictated by the equation representing hydrostatic balance. Log rho equals 3 log t minus 2 log m plus a constant. The minus 2 log m is part of the y-intercept. The lower the mass, the higher the intercept. So when we decrease m, the line shifts upward. Let's follow that new line. The star forms with low density and temperature and contracts, getting hotter and denser. But it crosses into the degeneracy zone even before hydrogen can ignite. It ends up as a sort of failed star, which cools off into oblivion like a white dwarf, but without ever having fused anything. More detailed calculations show that this happens when the mass is less than about 8% of the Sun's mass. Such an object is called a brown dwarf. It's a strange name. They're not literally brown. It's hard to say what color they are because most of their power comes out as infrared radiation. So all images are false color images anyways. I've seen false color images in which the brown dwarfs look green. We've just seen that the fate of an object of low mass is to become a brown dwarf or a white dwarf. What about a high mass star, say 10 solar masses? This time, relative to the Sun, the trajectory will be shifted down by 2 units. That's interesting because shifting down takes us away from the degeneracy zone. In fact, because of the kink in the boundary, the trajectory of a 10 solar mass star never enters the degeneracy zone. The reason is that the core of a massive star is hotter at any given density. It has to be to generate enough pressure to maintain equilibrium. And that high temperature ensures that gas pressure overwhelms degeneracy pressure all the way up to the critical density and beyond. If we dial the mass back down, somewhere in between 1 and 10 solar masses, there's a special case in which the star's path just skims the boundary. This special mass is none other than the Chandrasekhar mass, the maximum possible mass of a white dwarf. A star of higher mass will keep contracting, igniting heavier and heavier nuclei, burning ever hotter, trying ever more desperately to prevent gravitational collapse. But it can't hold out forever. Think back to our crash course in nuclear physics and the binding energy curve. Fusion only releases energy for nuclei on the left side of the peak. More massive nuclei prefer fission to fusion. So once you fuse your way up to iron and nickel at a temperature approaching 10 billion Kelvin, that's the end of the fight. Nuclear fusion is spent. Once the star crosses that boundary, which we'll mark with an ominous black line, gravity acts unopposed. In less than a second, the core collapses and what then? Does it become a black hole? Not necessarily, but I'll save that story for the next lecture. For now, I need to add one more detail to the chart. There's another possible source of pressure, radiation pressure. That's the pressure arising from the photons, which, like gas particles, carry momentum and thereby exert a pressure. But it obeys a different formula than the ideal gas law. Radiation pressure is proportional to temperature to the 4th power, a much stronger dependence on temperature. What that means is that even though radiation pressure is negligible in Sun-like stars, if we make the core hot enough, radiation pressure will dominate. To figure out where that happens in the chart, we should set the ideal gas pressure equal to the radiation pressure and solve for rho versus T. We won't take the time to do that, but I'll show you the result. The zone where radiation pressure dominates is in the lower right, with a boundary of slope 3. That's another no-go zone for a star. A star supported by radiation pressure throughout its interior turns out to be unstable. The intense radiation from such a star would push itself apart. That helps to explain why we almost never find stars more massive than about 100 solar masses. Such stars are in the radiation zone. And with that, we've seen all the most important events of stellar evolution from our vantage point in the center of the star. Now let's watch the same drama from the outside, the part that we can observe directly with our telescopes. Instead of plotting core temperature and density, we'll draw a Hertzsprung-Russell diagram, luminosity versus effective temperature, which is the surface temperature, the photosphere temperature, not the core temperature. And following hallowed tradition, the temperature axis is backwards. And remember, this kind of chart also encodes the radius of the star, with big stars in the upper right, small in the lower left. So let's start with the solar mass of hydrogen and helium. It contracts under its own gravity and forms a sphere. How do its luminosity and effective temperature and radius change with time? This turns out to be much more complicated than trying to explain what's happening in the core, because we need to consider not just pressure and gravity, but also how fast the energy flows to the surface. We need to know how the opacity of the gas depends on temperature and density, and we need to model convection, energy transport, by patterns of circulating material inside the star, with rising bubbles of hot gas and sinking bubbles of cooler gas. We also need to account for the changing composition of the star. For example, even after the core runs out of hydrogen, there's still hydrogen further up toward the surface, and that higher altitude hydrogen keeps burning long after the core has fizzled out. What happens is you get a shell of burning hydrogen surrounding the core of inert helium. This so-called shell burning process turns out to be less stable than core burning. Shell burning completely transforms the structure of a star, turning it into a giant. We can't understand all that with order of magnitude calculations. There are too many crisscrossing physical principles. So there's no substitute for writing down all the equations and solving them on a computer. For the rest of this lecture, I will simply narrate what happens based on what we've learned from those detailed calculations. We start the story of a solar mass star as before, with a clump of low-density gas being pulled together by gravity. It starts out large in the upper right of the Hertzsprung-Russell diagram, and for 10 million years or so, it contracts while maintaining a nearly constant effective temperature of 3,000 or 4,000 degrees. Then it swings to hotter temperatures. The underlying reason is that convection stops being as important, which is a non-obvious consequence of the fact that deep down inside, hydrogen has begun fusing. The star has reached the main sequence. It settles in for 10 billion years of steady hydrogen fusion. The main sequence makes a diagonal stripe in the diagram. Higher mass stars sit further up and to the left. Lower mass stars are further down and to the right. Now let's continue following our one solar mass star. When the innermost 10% of the star's mass has been converted to helium, the star leaves the main sequence and starts the shell burning phase. Fusion occurs only within a layer of hydrogen surrounding the helium core. Now, because that burning shell is sitting on top of a contracting core, the shell gradually becomes denser and hotter, causing it to pump tons of power into the outer layers of the star, which causes them to expand a lot. The star swells up to become a red giant. At its maximum size, the Sun will grow 200 times larger than it is today, engulfing Venus and roasting the Earth. Its luminosity will be 2,000 times higher than today. Meanwhile, the core is still contracting. So the star develops a split personality. It becomes like a star within a star, a very dense hot core within a much larger puffball of cooler gas. Eventually, the core contracts enough for the helium to ignite. In stars like the Sun, this is an explosive process called the helium flash, a sudden burst of fusion related to the fact that the core is nearly degenerate when this happens. Then the star settles in for a steady phase of helium fusion. Now that fusion is happening in the core again, the size and luminosity go back down. The star takes up a position on what we would call in a logical world the helium main sequence, sort of like the old hydrogen-burning main sequence, but at higher luminosity. But the traditional name for that part of the Hertzsprung-Russell diagram is the horizontal branch, because stars of different masses all happen to have about the same luminosity during this phase. So together, they make a horizontal line. The star hangs out on the horizontal branch until the core runs out of helium. For the Sun, that'll take maybe 50 million years. Then comes a replay of the same events as before. The Sun starts shell burning again, this time with a helium shell surrounding an inert core of carbon and oxygen. This causes the star to swell up again and become a giant for the second time. At this point, the star is also starting to shed. The radiation pressure in the outer layers gets intense enough to push the gas out into space. A strong wind erupts from the surface. A star like the Sun loses about half of its mass during this stage. What that means is that by the time nuclear fusion halts, the star has expelled its outer layers and revealed that hot, dense core inside. A white dwarf. The star migrates all the way down to the lower left corner in the chart. Low luminosity, small size, and white hot. That's the fate of a solar mass star. As I've been emphasizing, the mass of a star is what determines its fate. A white dwarf can't exist with a mass larger than 1.4 solar masses, the Chandrasekhar mass. It would collapse under its own weight. But because of all that mass shedding during the giant phases, a white dwarf can emerge from a star that was initially much larger than the Chandrasekhar mass. That makes for a complicated relationship between a star's initial mass and its ultimate fate. The latest calculations show that even stars as massive as 8 solar masses end up with a core less massive than 1.4 and can become white dwarfs. Now, let's leave theory land for a while and ask a very important question. How do we know any of this stuff is true? I'd like to explain 2 lines of evidence. First, in the 1980s, an experiment confirmed that the Sun is powered by hydrogen fusion. This was done by detecting neutrinos, those ghostly particles that go along with the weak nuclear interaction. Some of the reactions involved in converting hydrogen to helium produce neutrinos. But neutrinos hardly interact with anything. That's why building a solar neutrino detector is a daunting challenge. The person who figured out how to do it was Raymond Davis. He knew that one of the reactions, postulated to occur within the Sun, should produce neutrinos with a high enough energy to transmute chlorine into argon. Unfortunately, that only happens on those very rare occasions when a neutrino actually hits a chlorine atom. So Davis built an enormous tank and filled it with 100,000 gallons of cleaning fluid that has chlorine in it. And he figured out how to sift through all that cleaning fluid and find the argon. And as if that weren't hard enough, he had to do all of this 5,000 feet underground, inside a disused gold mine. This was necessary to avoid the effects of cosmic rays, high-energy particles that impinge on the Earth and produce radioactivity that would have interfered with the experiment. Davis succeeded in detecting the neutrinos from the Sun, a feat that earned him the Nobel Prize. He also teamed up with a theoretician, John Bacall, to see if the detected rate of neutrinos agreed with the theories for the interior of the Sun. For a while, it seemed like the answer was no. But you know what? It turned out the neutrino is more complicated than particle physicists had thought. Neutrinos can change forms between 3 different kinds on their way to the Earth. And after making those corrections to the theory, everything hung together perfectly. So we really do understand what's happening at the center of the Sun. And as for the theory of how the Sun and other stars change with time, the most beautiful confirmation comes from observing star clusters. The stars in a cluster all formed from different clumps of the same cloud of material. So all the stars should have nearly the same age. A Hertzsprung-Russell diagram for a young cluster, like the Pleiades, shows that most of the stars are still on the main sequence. Stellar evolutionary models fit the data nicely, and they tell us that the age is about 100 million years. The diagram for an older cluster looks different. All the massive stars, which were in the upper left part of the main sequence, have swollen up and become giants. The only stars still surviving on the main sequence are the lowest mass, slowest burning ones. We also see stars on the horizontal branch, busy fusing helium into carbon and oxygen, and if we look hard enough, we can see loads of white dwarfs. These stars have been together for billions of years. Some clusters are as old as 13 billion years. They've seen it all: the collapse of the initial cloud of gas, the lengthy main sequence, the growth of the giants, the shedding of material through stellar winds, the revelation of white dwarfs and their colorful nebulae. These stars have also seen their most massive brethren undergo gravitational collapse. What happened to them will be the topic of the next lecture.